Welcome back to The Explainer. Today, we're diving straight into the invisible space barrier. This is a cosmic thought experiment that is absolutely going to rewire how you think about humanity's place in the universe. If you've ever looked up at the stars and wondered when we're finally going to get out there and explore them, buckle up. We are in for a wild, fascinating, and honestly, a slightly humbling ride. I want you to really think about this quote for a second. You will never leave the solar system. Nobody alive today will. And maybe no human ever. I know, right? It sounds incredibly bleak. We've been practically raised on science fiction promising us warp drives, sprawling galactic empires, and endless exploration. But this quote, it hits the nail on the head regarding a very real, intensely physical wall that we are currently crashing right into. So what's the deal? Why are we trapped behind an invisible barrier of nothingness? It's not a literal wall made of bricks, obviously, and it's definitely not some sci-fi alien force field. No, it's an invisible barrier made of inescapable fundamental physics. It's this brutal combination of distances so huge we literally can't comprehend them, and the horrifying reality of what actually happens when you try to move fast through a supposedly empty void. To really grasp this barrier, we've got to talk about speed. 635,000 kilometers per hour. That is the top speed of the Parker Solar Probe, which is the absolute fastest, most zippy little spacecraft humanity has ever managed to build. Now, you might be wondering, how did it even get that fast? Well, it's basically using a physics cheat code. It hurls itself around the gravity well of Venus, using the planet to slingshot and accelerate closer to the sun. It is an absolute engineering marvel. But to put that mind-blowing speed into perspective, let's look at how fast humans have actually gone. The absolute fastest a human being has ever traveled was way back in 1969. The Apollo astronauts were coming back from the moon at about 40,000 kilometers per hour. That is wildly impressive for sure, but compared to the Parker Solar Probe, they were practically taking a casual stroll. At 635,000 kilometers per hour, you could orbit the entire Earth in just 4 minutes. You could literally zip from the Earth to the moon in 36 minutes. So let's play this thought experiment out. Imagine we've got a crewed spaceship moving at that blistering Parker Solar Probe speed. A trip to Mars, which right now would take us 7 to 10 months, would take just 2 weeks. We'd fly right past Pluto in just about a year. Pretty amazing, right? We'd be totally conquering the solar system. But there is a massive, crushing catch waiting for us at the end of the line. To reach the Oort cloud, which is the actual edge of our solar system where open space really begins, we would have to travel for 2,500 years. That's the amount of time between the founding of the Roman Republic and today. And the scariest part of all that? There is absolutely nothing out there. Just an unimaginably massive void. Okay, so 635,000 kilometers per hour clearly isn't going to cut it. Let's break the rules, or at least let's push them to their absolute theoretical limits. What if we traveled at 20% the speed of light? We don't have magic warp drives, but a propulsion system using nuclear fusion or maybe antimatter could optimistically reach a substantial fraction of light speed. That's roughly 216 million kilometers per hour. This perfectly illustrates just how game-changing that kind of speed would be. At 20% the speed of light, we'd hit the edge of the solar system in just 3.5 days. We'd completely clear that massive Oort cloud in 8 years. And the big one, Alpha Centauri, our closest neighboring star system, is now just a 20-year journey. 20 years! That's perfectly manageable. We just cram a crew in a ship and they actually arrive within their own lifetimes. Problem solved, right? Well, unfortunately, no. Because this is exactly where we hit a very different kind of wall, the dust barrier. See, space is incredibly empty, sure, but it is not completely empty. There are stray, energetic particles, random clouds of gas, and tiny, seemingly cute little grains of dust just drifting out there in the dark. And when you are moving at 216 million kilometers per hour, cute little space dust becomes a massive, ship-shredding threat. The physics going on here are utterly terrifying. At 20% the speed of light, if your ship hits a single individual iron atom, it packs enough energy to carve microscopic bullet holes right into your hull. And the threat scales up violently. Hitting a single tiny grain of dust at this speed is literally like setting off a hand grenade right on the nose of your ship, instantly grinding away your protective shielding. And if you have the profound bad luck to hit a rogue rock the size of a golf ball, that releases more than double the energy of the nuclear bomb dropped on Hiroshima. This right here is the deadly physical speed limit of the universe. Without some magical sci-fi energy shielding, moving fast simply means dying fast. But hey, let's play along for a second. Let's say our brilliant engineers build some incredible regenerating shields, and our brave crew actually survives the dust barrier. They spend 20 years cramped together in a tiny metal box, they somehow manage not to murder each other, and they finally arrive at Alpha Centauri. They send a triumphant message back home, everyone on Earth holds their breath, only to find out that while the planets are pretty up close, they are completely deadly and totally uninhabitable. And this brings us to the next massive hurdle of deep space travel. If we zoom out and look at our stellar neighborhood, a sphere about 25 light-years in diameter around Earth, it sounds huge, right? But it's actually just 0.02% of the Milky Way. Inside this local bubble, we only have 34 stars and 6 brown dwarfs. It is a surprisingly empty, quiet pocket of the galaxy. Within that tiny bubble, out of those 34 stars, only 3 of them are actually similar to our Sun. And keep in mind, one of those 3 is our actual Sun, and another is Alpha Centauri A. The vast majority of our neighbors are red dwarfs. Red dwarfs are incredibly violent little stars, constantly tossing out massive solar flares that completely strip the atmospheres off their planets, making them vary from just regular deadly to super deadly. So finding a habitable zone out here is incredibly rare. And the really crucial point is this. Even if we do find a planet in a star's habitable zone, where liquid water could theoretically exist, it is a huge trap to just assume that means Earth-like. I mean, Earth is absolutely perfect for carbon-based life. But consider Mars for a second. Mars is technically right there in our Sun's habitable zone too. And Mars is a frozen, irradiated, completely barren wasteland. Just because a planet is sitting in the right spot mathematically doesn't mean it comes with a breathable atmosphere or warm oceans. I really love this quote from our source material because it just perfectly captures the tragic irony of this whole thought experiment. Imagine traveling your entire life and then arriving at a Mars. What a brutal letdown that would be. Think about it. You spend decades locked in a metal tube, braving the intense dust barrier, surviving the absolute void of space, only to step out onto a barren rock that you could have basically found right in your own cosmic backyard. The reachable destinations are mostly completely lame when it comes to sustaining human life. So let's synthesize everything we've looked at into 3 undeniable steps of our deep space reality. 1, the distances are so incomprehensibly vast that our monkey brains literally cannot process them. 2, even if we somehow generate enough power to go really fast, the dust barrier creates a brutal physical speed limit. And 3, even if we miraculously survive the journey, almost all reachable destinations within a single human lifetime are completely barren or totally lethal. This, altogether, is the invisible space barrier. So, the natural question becomes, are we just hopelessly underpowered forever? Are our rockets, supercomputers, and even theoretical nuclear fusion reactors just never going to be enough? Are we permanently locked into our solar system as a species? Well, if we judge entirely by what we know today, the answer looks like a pretty depressing yes. But, and this is a really massive but, humans are famously, hilariously terrible at predicting the future limits of our own technology. Get this, on October 9th, 1903, the New York Times published this highly confident editorial stating it would take humans 1 to 10 million years to build flying machines. Just 69 days later, the Wright brothers successfully flew at Kitty Hawk, and just 66 years after that, humanity landed on the moon. What this brilliantly illustrates is that relying solely on our current understanding of physics to predict our ultimate limits is usually a one-way ticket to looking really foolish in the history books. The truth is, we don't need a slightly better rocket. We need an overwhelmingly transformative technology. We need something that is as unimaginable to us right now as flying to the moon would have been to a prehistoric hunter-gatherer. So what is that technology waiting for us in the future? Will we figure out how to cure biological aging so a 1,000-year space journey feels like a breeze? Will we discover entirely new physics that lets us bypass the space barrier entirely? We genuinely don't know yet. But it leaves us with an incredibly exciting thought to chew on. The hard limits of today are just the starting lines for tomorrow. Keep wondering, keep exploring, and we'll see you in the next explainer.